Hi everyone, I will present our new work, Fine-Grained Multi-Core Stream Processing on Integrated Architectures, co-authored by Feng Zhang, Chenyang Zhang, Yang, Shuhao Zhang, Bingsheng, Wei Lu, and Xiaoyong from Renmin University of China, Singapore University of Technology and Design, and National University of Singapore. Here's the outline of my presentation. Nowadays, optimizing the performance of stream processing systems has been a hot research topic. Multi-core stream processing is very common in real-world applications, including cluster monitoring, anomaly detection in smart grids, and road tolling systems. A query is a way of requesting information from a stream with continuous semantics. A multi-query refers to the usage of multiple queries on the same machine. Accelerating multi-query stream processing with GPUs has been shown to be very effective. GPUs consist of a large number of lightweight computing cores, which are naturally suitable for data-intensive multi-core stream processing. There are some new opportunities brought by integrated architectures. The figure shows the difference between the integrated architecture and the discrete architecture. We can observe that the CPU and the GPU in the integrated architecture share the same system memory, while they use independent memory in the discrete architecture and transfer data through PCI-e. The unified physical memory in integrated architecture can eliminate data transmission cost and therefore guarantees fine-grained cooperation between the CPU and the GPU. So, there is a new opportunity to provide a fine-grained workload assignment in stream processing. To see whether fine-grained workload assignment can improve performance, we explore the device preference of each operator in stream processing, and the result is shown in the table. We find that device preference varies for different operators. So based on integrated architecture's feature and this observation, we propose FineStream, a fine-grained multi-core stream processing on integrated architectures. And let's see some background knowledge about window-based relational stream processing with SQL. The data stream is a sequence of tuples, and the window is a tuple unit to be processed. An operator is a processing unit. In our work, we support projection, selection, aggregation, group by, and join operator. And the query is a set of operators executed on the window. Our work has some challenges. The first one is application topology combined with architectural characteristics makes operator assignment and scheduling complicated. The relation among operators in a query is very complex and is organized in a directed acyclic graph. And architectural characteristics and device preference of operators should also be considered when assigning operators. And the second challenge is multi-core plan with shared main memory. The bandwidth pressures caused by operators are different, and memory bandwidth requirement becomes larger when co-running operators. Preferred memory access patterns of the CPU and the GPU are different. The third challenge is adjustment for dynamic workload. Workload change detection and computing resource adjustment are finished on the fly, so they'll need to be done in a lightweight manner. Query plan may need to be updated adaptively, and online stream processing needs to be served efficiently during adaptation. Adjustments among different streams need to be considered to improve performance. We designed FineStream to solve all these challenges. There are 4 major parts in FineStream framework. When the engine starts, the online profiling module processes several batches using only the CPU or the GPU to gather useful data to analyze memory bandwidth and throughput. Then the performance model module uses the collected data to build models for queries with both the CPU and the GPU. After the performance model is built, the dispatcher assigns stream data and operators to proper processors on the fly in a fine-grained way. Then the CPU and the GPU start to do the operators, and the multi-query handling module starts to work if multiple queries are detected. And here's the solution to the above-mentioned challenges. The solution for challenge 1 is the online profiling module estimates the performance by sampling on a small number of batches, and the dispatcher dynamically puts the operators on the preferred devices. The second solution is the bandwidth factor is considered when building the performance model, which can be used to guide the parallelism for operators with limited bandwidth. The third solution is the online profiling analyzes the dynamic workloads and FineStream responds to dynamic workloads with different strategies based on the analysis. In the performance model module, we consider 2 kinds of parallelism. For intra-batch parallelism, we consider branch co-running, which means executing independent branches in parallel, and we optimize branch scheduling shown in the right picture. We reassign branch 3 to improve the total performance. And for inter-batch parallelism, we consider batch pipeline, which means processing different batches in pipelines. It is shown in the picture below. We partition the query into phases, like in figure A, phase 1 and phase 2, and we process phases in pipeline. To handle dynamic workload, we propose query plan adjustment. FineStream generates several possible alternative query plans. During stream processing, FineStream monitors the performance and switches to another alternatives if performance decreases. And the resource reallocation is lightweight. When the workload ingestion rate of a branch decreases, FineStream transfers the compute resource to the other branches. This strategy is lightweight because FineStream monitors the ingestion rate during batch loading. FineStream supports multi-query. There are 2 situations. One is multi-query in single stream. FineStream organizes operators from different queries into the same deck since they are from single stream, and then use the performance model to distribute the computing resources to operators. We propose an operation method called operator sharing shown in the figure. The operator 1 and operator 2 are the same in query 1 and 2, and therefore their results can be shared. In the second situation, multi-core in multi-stream, the monitor thread identifies the input streams and collects necessary performance data. And then, based on the gathered data, FineStream distributes computing resources to the operators of cores targeting different streams. That's all the main design of FineStream. And then we evaluate FineStream compared with three baselines. The first one is best single device performance, denoted as single. And the second one is static FineStream, denoted as static. The third one is a state-of-the-art window-based stream processing engine for discrete architectures, Sabre. The benchmarks we used is the benchmarks in Sabre. We first evaluate the multi-core performance. From the three figures, we can observe that FineStream outperforms Single and Sabre for throughput and latency. And for dynamic workloads, FineStream outperforms the static FineStream. For single core performance, FineStream also outperforms Single and Sabre, and its GPU utilization is the highest. We also compare FineStream in integrated architecture with Sabre in discrete architecture. The throughput in discrete architecture is higher. However, FineStream in integrated architecture has higher price-throughput ratio and energy efficiency, which means that stream processing with FineStream in integrated architecture is cheaper. Therefore, integrated architecture is. Finally, I conclude what we do in this work. We propose the first fine-grained window-based relational stream processing framework that takes the advantages of the special features of integrated architectures. We name it FineStream. We develop lightweight query plan adaptation to handle dynamic workloads. We develop operator sharing and stream ingestion rate detection to handle multi-query. And then we evaluate FineStream and make a comparison with state-of-the-art studies. That's all about our work. Thank you for your listening.